In physics and mathematics, observing a system flooded with extreme, unpredictable variance usually means watching it fall apart. But under specific topological conditions, that chaos hits an invisible geometric container and freezes into a perfect, predictable lattice. Modern physics frequently hits a wall known as an epistemological rupture. This is a specific failure point where standard mathematical formulations break down, typically because continuous manifolds lack the compact, rigid emdries needed to contain them. At this boundary, thermodynamic variance, energetic fluctuations within a system, overwhelms the finite parameters of the model. This creates a state of presumed unboundable noise. The theory of infinity, or TOI framework, seeks to resolve this chaotic variance into a deterministic scale-invariant structure. The mechanism for achieving this resolution is the friction versus fiction protocol. It treats statistical anomalies not as random errors, but as structural certainties generated by underlying symmetry. A recent computational audit tested this by tracking extreme Pareto variance, a distribution characterized by heavy-tailed, unpredictable values. The goal was to observe if this variance would collapse into absolute discrete invariance, followed by a dimensional lift into a continuous state. Within this framework, extreme mathematical chaos acts as the structural heat required to generate a bounded reality from an infinite context. The experiment begins inside a finite-step accumulator. This computational engine is subjected to high-variance random walks via a Monte Carlo mill, which uses repeated random sampling to compute structural results. This diagram illustrates the topological violence of the simulation. On the left side, the variance clouds represent the Fibonacci core sequence, swinging wildly between 38.08 and 46.57. The core Tribonacci sequence experienced even more aggressive three-dimensional volatility, oscillating between 56.04 and 72.42. This high variance wandering through phase space is defined as Brownian topological motion. This motion represents the kinetic energy of the system, the active friction produced by discrete integers reacting as they press against continuous scaling constraints. The system resolves this friction using the law of large numbers, functioning within the rules of the friction versus fiction protocol. Exhaustive temporal accumulation acts as a mathematical grinder. As stochastic noise is processed through the lattice, variance is steadily eliminated. The empirical output perfectly collapses into the pre-calculated discrete geometric means, 42.4 for the Fibonacci set and 62.2 for the Tribonacci set. This collapse validates topological ergodicity. It proves that stochastic wandering within a golden set is ultimately chained to the immovable geometric center of the integers. To understand the precision of these outputs, we have to look past the macro resolution of 42.4 and 62.2. We must examine the microscopic gap between these outputs and the absolute mathematical center. The engine calculates specific logarithmic residuals for the Fibonacci and Tribonacci manifolds. A logarithmic residual measures the tiny, quantifiable divergence between a finite physical result and a pure theoretical limit. This gap follows the precedent of the Pell-Lucas crossing. When a finite data packet approaches a continuous mathematical limit, it leaves a precisely quantified gap. At this crossing, a finite monitor converges toward a fixed quantity, but leaves an intentional structural gap, which is held between two-sided mathematical bounds. The ledger maintains a strict distinction here. Finite monitored anomalies are never confused with universal exact identities. The gap is a defined structural area, not a random error. This historical precedent directly explains the residuals we observed in the Fibonacci and Tribonacci accumulators.
These logarithmic residuals are the thermodynamic footprints of a finite-step accumulator physically pressing against a continuous mathematical limit. This numerical discrepancy represents a structural boundary required for the system to maintain continuity across discrete and continuous domains. With the discrete invariance verified, the audit moves to a secondary challenge, the transition from discrete variance to a continuous phase friction experiment. The core mechanic of this transition involves injecting a fractional constant, the natural log of phi, into the stochastic engine. Phi, or the golden ratio, is the universal geometric scaling constant, approximately 1.618. We decompile this operation to reveal its underlying structure. We start with the expression, a discrete integer variable, x, raised to the power of the natural log of phi. Using the natural base e, this expands to e raised to the power of the natural log of x times the natural log of phi. Because multiplication within an exponent is commutative, we algebraically swap these terms. The natural log of x and the natural log of phi trade places without changing mathematical truth. Since e raised to the natural log of phi is an exact inverse, the stack collapses to phi raised to the natural log of x. This algebraic identity reconfigures the relationship between the discrete integer and the golden ratio. The integer x shifts from its position as the base into the exponent, while the golden ratio takes over as the foundational metric. This operation, the topological base swap, replaces the standard base 10 integer foundation with the universal geometric metric of phi. The stochastic engine now converts discrete integers into continuous, transcendental golden frequencies. In this continuous domain, the integers function as fractional weights that determine the amplitude of the golden frequency. Once the base swap is executed, we can observe the macroscopic outputs of these newly lifted continuous manifolds. This table shows the results of the lift. In the Fibonacci set, high variance inputs are smoothed into a logarithmically damped continuous scale. Calculating the arithmetic mean of these fractional weights, the exact geometric center resolves to 5.595. In the Tribonacci set, the larger and more volatile integer inputs yield a wider spread of continuous frequencies after the exponential lift. The geometric center for this lifted Tribonacci phase space resolves to 6.536. These specific coordinates, 5.595 and 6.536, are the pre-registered fractional topological rails. By converting discrete sets to continuous transcendental powers, the system proves that unbounded infinity contains inherent fixed-point geometric boundaries. This continuous fractional domain remains anchored to the discrete domain through specific symmetry laws. This anchor is evidenced by the Routh-Arron hinge, where successive Fibonacci nodes share perfectly conserved prime factorizations, rigidly linking the discrete integers to the continuous scale. We can verify these continuous phase models by looking at recent quantum chemistry experiments mapping the behavior of physical molecules. Researchers recently synthesized a ring molecule that exhibits a half-Mobius electronic topology achieved through atomic manipulation with a scanning probe microscope. This physical molecule twists by exactly pi in one complete circumnavigation, exhibiting a precise four-state phase orbit known as quarter-turn monotony. This physical behavior mirrors the exact continuous phase sorting architecture predicted by the theory's mathematical limit laws. The fractional rails of 5.595 and 6.536 establish the geometric boundaries a thermodynamic system adheres to when scaling through continuous phase space. The base swap proves that infinite chaotic variance, when confined by a golden set, is strictly and physically subservient to the immovable bedrock of the integers.